Welcome to the video series Data Science for Beginners. Data science can be intimidating, so I'll introduce the basics here without any equations or computer jargon. In this first video, we'll talk about the 5 questions that data science can answer. Data science uses numbers and names, which are also called categories or labels, to predict answers to questions. And it might surprise you, but there are really only 5 questions that data science answers. Is this A or B? Is this thing weird? How much or how many? How is this data organized? And what should I do next? Each one of these questions is answered by a separate family of machine learning methods called algorithms. It might be helpful to think about an algorithm as a recipe. You put your data as the ingredients, and the algorithm tells you how to combine and mix them to get an answer. And computers are like a blender. They do most of the hard work of the algorithm for you, and they do it really fast. So let's start with the question, is this A or B? This family of algorithms is called classification, and when there's only 2 choices, it's 2-class classification. It's useful for any question that has just a couple answers. For example, will this tire fail in the next 1,000 miles? Yes or no? Which brings in more customers, a $5 coupon or a 25% discount? This question can also be rephrased to include more than 2 options. Is this A or B or C or D? And this is called multi-class classification. It's useful when you have several or even several thousand possible answers. Multi-class classification will go through and choose the most likely one. The next question the data science can answer is this weird? This question is answered by a family of algorithms called anomaly detection. If you have a credit card, you've already benefited from it. Your credit card company analyzes your purchase pattern so that they can alert you to possible fraud. Charges that are weird might be a purchase at a store where you don't normally shop, or buying an unusually pricey item. This question can be useful in lots of ways. For instance, you might want to know, is this pressure gauge reading normal, especially if it's in the tire of your car? You might want to know, is this message from the internet typical? Anomaly detection flags unexpected or unusual events or behaviors, and it can give you a clue where to look for problems. Machine learning is also used to answer the question, how much or how many? Algorithms that answer these questions are called regression, and they make numerical predictions, such as, what will the temperature be on Tuesday? What will my 4th quarter sales be? They help answer any question that asks for a number. Now, the last 2 questions that data science can answer are a little bit different. Sometimes you just want to understand the structure of a data set, and you ask, how is this organized? For this question, you don't have examples that you already know the outcomes for. Now, there are a lot of ways to tease out the structure of the data. One is called clustering, and it separates the data into natural clumps for easier interpretation. And with clustering, there's no one right answer. Common examples of clustering questions are, which viewers like the same types of movies? Or which printer models fail in the same way? By understanding how data is organized, you can better understand and predict behaviors and events. The last question, what should I do now, uses a family of algorithms called reinforcement learning. Reinforcement learning was inspired by how the brains of rats and humans respond to punishment and rewards. These algorithms learn from outcomes and decide on the next action. Typically, reinforcement learning is a good fit for automated systems that have to make lots of small decisions without human guidance. Questions it answers are always about what action should be taken, usually by a machine or a robot. Examples are, in a temperature control system, adjust the temperature up or down or leave it where it is. In a self-driving car, at a yellow light, brake or accelerate. Or with a robot vacuum cleaner, keep vacuuming or go back to the charging station. Reinforcement learning algorithms gather data as they go, learning from trial and error. So that's it, the 5 questions data science can answer. Be sure to check out the other 4 videos in the Data Science for Beginners series for Microsoft Azure Machine Learning. Welcome to how to know if your data is ready for data science. This is the 2nd video in the series, Data Science for Beginners. Before data science can give you the answers that you want, you have to give it some high-quality raw materials to work with. Just like making a pizza, the better ingredients you start with, the better the final product. So in the case of data science, there are some ingredients we need to pull together. We need data that's relevant, it's connected, accurate, and we need to make sure we have enough of it. So the first ingredient we need, data that's relevant. So take a look at the table on the left. We met 7 people outside of bars in Boston and measured their blood alcohol level, the Red Sox batting average in their last game, and the price of milk in the nearest convenience store. This is all perfectly legitimate data, but its only fault is that it isn't relevant. There's no obvious relationship between these numbers. If I gave you the current price of milk and the Red Sox batting average, there's no way that you could guess my blood alcohol content. Now, check out the table on the right. This time we measured each person's body mass and counted the number of drinks they've had. The numbers in each row are now relevant to each other. If I gave you my body mass and the number of margaritas I've had, you could make a pretty good guess at my blood alcohol content. The next ingredient is connected data. Here's some relevant data on the quality of hamburgers, grill temperature, patty weight, and the rating in a local food magazine. But notice the gaps in the table on the left. Most data sets are missing some values, and it's common to have holes like this, and there are ways to work around them. But if there's too much missing, your data starts to look like Swiss cheese. Looking at the table on the left, there's so much missing data, it's hard to come up with any kind of relationship between grill temperature and patty weight. This is an example of disconnected data. The table on the right, though, is full and complete, a great example of connected data. The next ingredient we need is accuracy. So here are 4 targets we'd like to hit with arrows. Look at the target in the upper right. We get a tight grouping right around the bullseye. That, of course, is accurate. And then if you look at the next target on the lower right, oddly, in the language of data science, our performance on that target is also considered accurate. If you were to map out the center of these arrows, you'd see that it's very close to the bullseye. The arrows are spread all around the target, so they're considered imprecise, but they're centered around the bullseye, so they're considered accurate. The target in the upper right is both accurate and precise, so that's a good job. Now look at the upper left target. Here, our arrows hit very close together, a tight grouping. They're precise, but they're inaccurate because the center is way off the bullseye. And of course, the arrows in the bottom left target are both inaccurate and imprecise. This archer needs a bit more practice. Finally, ingredient number 4. We need to have enough data. If you think of each data point in your table as being a brush stroke in a painting, then if you only have a few of them, the painting can be pretty fuzzy. It's hard to tell what it is. If you add some more brush strokes, then your painting starts to get a little sharper. And you know when you have just barely enough, you can start to see the pattern and make some broad decisions. I look at this and I think, is this somewhere I might want to visit? It looks bright, the water looks clean. I decide, yes, that's where I'm going on vacation. As you add more data, the picture becomes clearer and you can make even more detailed decisions. Now I can look at the 3 hotels on the left bank. I say, you know, of those 3, I really like the architectural features of the one in the foreground. I'll stay there right on the 3rd floor. With data that's relevant and connected, accurate, and with enough of it, we have all of the ingredients we need to do some high-quality data science. Be sure to check out the other videos in Data Science for Beginners from Microsoft Azure Machine Learning. Welcome to the third video in the series, Data Science for Beginners. In this one, you'll get some tips for formulating a question you can answer with data. You might get more out of this video if you first watch the two earlier videos in this series, the 5 questions data science can answer, and is your data ready for data science? We've talked about how data science is the process of using names and numbers to predict an answer to a question. You can also call names categories or labels. Now the trick here is that it can't be just any question. It has to be a sharp question. A vague question doesn't have to be answered with a name or a number, but a sharp question must. Imagine you found a magic lamp with a genie who will truthfully answer any question you ask. But it's a mischievous genie, and he'll try to make his answer as vague and confusing as he can get away with. You want to pin him down with a question so airtight that he can't help but tell you what you want to know. If you were to ask a vague question like, "What's going to happen with my stock?" the genie might answer, "The price will change." It's a truthful answer, but it's not very helpful. But if you were to ask a sharp question like, "What will my stock sale price be next week?" the genie can't help but give you a specific answer and predict a sale price. Now, once you formulate your question, check to see whether you have examples of the answer in your data. So if your question is, "What will my stock sale price be next week?" then we have to make sure that our data includes the stock price history. If our question is, "Which car in my fleet is going to fail first?" then we need to make sure that our data includes information about previous failures. These examples of answers are called a target. A target is what we are trying to predict about future data points, whether it's a category, a name, or a number. If you don't have any target data, you'll need to get some. You won't be able to answer your question without it. Now, to take this to the next level, sometimes you can reword your question and get a more useful answer. The question, "Is this data point A or B?" predicts the category of something. And then to answer it, we use a classification algorithm. The question of "how much" or "how many" predicts an amount. And to answer that, we use a regression algorithm. To see how we can transform one of these into the other, let's look at the question, which news story is the most interesting to this reader? It asks for a prediction of a single choice from many possibilities. In other words, is this A or B or C or D? Is it this story or that one or that one or that one? And it would use a classification algorithm. But this question may be easier to answer if you reword it, such as, "How interesting is each story on this list to this reader?" Now you can give each article a numerical score, and then it's easy to identify the highest scoring article. This is a rephrasing of a classification question into a regression question. How you ask a question is a clue to which algorithm can give you an answer. You'll find that certain families of algorithms, like the ones in our news story example, are closely related. You can reformulate your question to use the algorithm that gives you the most useful answer. But most importantly, ask the sharp question, the question you can answer with data, and be sure you have the right data to answer it. We talked about some basic principles for asking a question that you can answer with data. Be sure to check out the other videos in Data Science for Beginners from Microsoft Azure Machine Learning. Welcome to the fourth video in the Data Science for Beginners series. In this one, we'll build a simple model and make a prediction. A model is a simplified story about our data. I'll show you what I mean. Say I want to shop for a diamond. I have a ring that belonged to my grandmother with a setting for a 1.35 carat diamond, and I want to get an idea of how much it will cost. I take a notepad and a pen into the jewelry store, and I write down the price of all the diamonds in the case and how much they weigh in carats. Starting with the first diamond, it's 1.01 carats and $7,366. Now I go through and do this for all of the other diamonds in the store. So notice that our list has two columns. Each column has a different attribute, weight in carats and price, and each row is a single data point, represents a single diamond. We've actually created a small data set here, a table. Notice that it meets our criteria for quality. The data is relevant. Weight is definitely related to price. It's accurate. We double-checked the prices that we wrote down. It's connected. There are no blank spaces in either of these columns. And as we'll see, it's enough data to answer our question. Now we'll pose our question in a sharp way. How much will it cost to buy a 1.35 carat diamond? Our list doesn't have a 1.35 carat diamond in it, so we'll have to use the rest of our data to get an answer to the question. The first thing we'll do is draw a horizontal number line called an axis to chart the weights. The range of the weights is 0 to 2. So we'll draw a line that covers that range and put ticks for each half carat. Next, we'll draw a vertical axis to record the price and connect it to the horizontal weight axis. This will be in units of dollars. Now we have a set of coordinate axes. We're going to take this data now and turn it into a scatter plot. This is a great way to visualize numerical data sets. For the first data point, we eyeball a vertical line at 1.01 carats. Then we eyeball a horizontal line at $7,366. Where they meet, we draw a dot. This represents our first diamond. Now we go through each diamond on this list and do the same thing. When we're through, this is what we get. A bunch of dots, one for each diamond. Now if you look at the dots and squint, the collection looks like a fat fuzzy line. We can take our marker and draw a straight line through it. By drawing a line, we created a model. Think of this as taking the real world and making a simplistic cartoon version of it. Now the cartoon is wrong. The line doesn't go through all the data points, but it's a useful simplification. The fact that all the dots don't go exactly through the line is okay. Data scientists explain this by saying that there's the model, that's the line, and then each dot has some noise or variance associated with it. There's the underlying perfect relationship, and then there's the gritty, real world that adds noise and uncertainty. Because we're trying to answer the question, how much? This is called a regression. And because we're using a straight line, it's a linear regression. Now we have a model and we ask it our question. How much will a 1.35 carat diamond cost? To answer our question, we eyeball 1.35 carats and draw a vertical line. Where it crosses the model line, we eyeball a horizontal line to the dollar axis. It hits right at $10,000. Boom, that's the answer. A 1.35 carat diamond costs about $10,000. It's natural to wonder how precise this prediction is. It's useful to know whether the 1.35 carat diamond will be very close to $10,000 or a lot higher or lower. To figure this out, let's draw an envelope around the regression line that includes most of the dots. This envelope is called our confidence interval. We are pretty confident that prices fall within this envelope because in the past, most of them have. Now we can draw two more horizontal lines from where the 1.35 carat line crosses the top and the bottom of that envelope. Now we can see something about our confidence interval. We can say confidently that the price of a 1.35 carat diamond is about $10,000, but it might be as low as $8,000, and it might be as high as $12,000. We did what data scientists get paid to do, and we did it just by drawing. We asked a question that we could answer with data. We built a model using linear regression. We made a prediction complete with a confidence interval, and we didn't use math or computers to do it. Now, if we'd had more information like the cut of the diamond, color variations, how close the diamond is to being white, the number of inclusions in the diamond, then we would have had more columns. In that case, math becomes helpful. If you have more than 2 columns, it's hard to draw dots on paper. The math lets you fit that line or that plane to your data very nicely. Also, if instead of just a handful of diamonds, we had 2,000 or 2 million, then you can do that work much faster with a computer. Today we've talked about how to do linear regression, and we made a prediction using data. Be sure to check out the other videos in Data Science for Beginners from Microsoft Azure Machine Learning.